All right, our last segment of this talk, afterwards a link and some thanks, is just to talk about convergence and divergence of sequences and show that it's really exactly the same concept. And in fact, a lot of the stuff we've said earlier applies directly and simplifies our approach to convergence and divergence of sequences. Here's the picture you'd typically see in a textbook when you talk about the definition of limit n goes to infinity a n equals L. The concept is, I've animated it here, you can play with it as usual. No matter how small you make epsilon, great, you can make n big enough so that the rest of the terms, so to speak, all lie within epsilon of the limit. There you go. Anyone who's thinking ahead would know I totally object to this picture on one main basis. My basis is the domain. I mean, a sequence is a function at the end of the day. The domain, the ends axis, and the axis for the outputs have been stuck on top of each other, which is, I think, a bit bad. We should view a sequence just like we view a function. So if I split those off, I get this picture. Here's the n values I'm going to toss into the sequence. Here it tells me what heights they are, but don't forget to push them all the way over to the axis, see the actual values of the sequence that come out. If you just look at the vertical axis here, the output axis, you should see a picture you recognize. What's the concept for sequences? Well, the thing we always do with the sequence concerning convergence and divergence is plot all the terms of the sequence. And then you can picture a plus infinity squeezing to the right on the n-axis here, and then take away more and more initial terms and just look at what happens. It's as simple as that. In fact, I'm going to take away the axes. Here is all the terms of that sequence. I mean, as far as the computer can get them anyway. Here's all the terms. Now, I'm going to start taking away the first, the second, the third, take away more and more initial terms of the sequence and ask yourself what you see. And what you see is exactly the same picture of convergence as we've seen this whole day. That is the convergence. The sequence an, we always do the same thing with sequence. Take off more and more initial terms to let it squeeze. Fits into that model of L plus minus dot. Converges to L, just like all the other things did. In fact, there you go. You should see a similarity. Not much to play with here. You should see that the blues are acting like the reds. Now we could go back and draw the whole picture and see that in action. Let's go ahead and do it. You're throwing away more and more terms. You shouldn't be just moving that in. You should be actively throwing out those terms. And when you throw them out, the rest of the terms should be squeezing closer and closer and closer to L. Again, the sequence is not increasing or decreasing, but the squeezing happening in the outputs is monotonic. This monotonicity is very, very important, and it's part of the definition. It really simplifies considerations. You see the exact squeezing you want, and you can work up to the full definition of limit of sequences this way. To carry along, divergence, we see what infinity looks like. Divergence, we should see infinity for a sequence that diverges to infinity. Again, here's the standard picture you might see in a calculus book. Set your target of m. You can find an n such that all the terms to the right lie above or whatever. And again, we can animate this if we like on this picture. Make n bigger if you like. How big does n have to be? Well, we'll go a bit further, and there you go. And if m's a little bit bigger, well, then n's a little bit bigger. It's the usual picture. So nothing's changing logically. It's just a bit of a mindset or approach I'd like to change. If we split the axes like I'd like to in general, inputs, outputs, and we just do with sequences what we do, I'll get rid of it, take away more and more initial terms and just look at what the rest do. Well, what the rest do is actually a nice pattern we've seen before, and it shouldn't be surprising. As you take away more and more terms, the rest of the terms end up as being larger and larger and larger positive numbers, just like our model for plus infinity. If you like, we can rewind it all and bring out the graph. You can see it in the graph as well. As you throw away more and more terms on the graph, don't forget to push them over to the output, though. The results push to larger and larger and larger positive numbers, just like your standard model of positive infinity does, right? You should see a similarity there. You should see your usual picture happening, okay? In one case, it's the standard positive infinity. In the other case, it's the rest of the terms of your sequence, and I'll pause here for a second. Notice it doesn't matter whether the sequence itself, whether its terms are monotonic or not. These terms are all over the place. But the rest of the terms, if you keep on throwing terms away, do monotonically, the rest as a set, push upward and upward and upward, so it's really not so bad. Let me end there and just mention all these animations. If you found this set of YouTube videos, you may have already found the site. Nearnumbers.net has these first 4 animations are already up, and the next 4 I'll put up shortly. They're freely available online, so do with as you please. And please do. Before I finish, I just want to say the thanks that I had to say really quickly when I gave the talk for real, but I'll put it online for the record. Thanks to Charlie for inviting me, the MAA, and the organizer of this conference that I gave the talk originally at, for the opportunity to speak. And to skip to the bottom, thank you for the entire audience for your attendance and your patience, because we went over time and I didn't finish the talk. But there were an awful lot of good questions and good discussion going on. Also, just to give them credit where it's due, my department at Middlebury College has really given me a lot by giving me the pedagogical freedom to experiment and do things with my calculus courses that eventually led to this whole approach. And finally, my wife for putting up with not only me preparing the talk and updating the animations, but me going through the hassle of trying to put together a sequence of YouTube videos to redo the talk. And thank you very much. Again, my name is Frank Swenton. I'm at Middlebury College. I'd be happy to entertain any questions, comments, complaints, arguments about this. It's something that I hope will eventually take hold in the calculus curriculum eventually. I can't say the word eventually enough. I think it's going to be slow. I think there's going to be a lot of resistance, but there's really no loss because the definitions stay the same, but I've used it with my students for years, and there's a whole lot of gain in terms of their ability to explore and understand. Thank you very much.